Hello, welcome to today's lecture. So we're starting module 4. We are on 4.1. What are the objectives? So objectives of today's lecture, actually, again, we are dealing with scatter plots and we're trying to find patterns in our collection. So finding patterns in our data, in our collection. And the second thing that we're going to do, we're going to actually construct and build an exponential model. What is an exponential model? Very well. So before going over the definition, let us review what we learned so far. So in module 3, we learned about linear models. Linear models. So what's a linear model? A linear model is defined as y hat equals to mx plus b. It means that you can grab your data and you can actually find an increasing or decreasing line connecting those data. In this case, you have m, or the rate of change of your line or the slope, and b is y-intercept. For example, if you have your independent variable like x, and variable y depends on variable x, and suppose you have these data in this collection, you have a scatter plot, of course you have some noise somewhere, then we can actually use a fitted line with equation y hat equals to mx plus b. Last time we learned how to use the online calculator, how to go to different online websites like Alculo, and those websites actually help us to write equation of the line and actually graph the linear model. What was our point? What was our goal? Our goal was to take this equation, take this model, and make some predictions. So our goal was to predict other y values. Now I expect you to ask, what if I don't have a linear model? What if I have a non-linear model? How can I construct the mathematical model for that scatter plot and the pattern in my collection? For example, suppose you have this collection here. Here you have your x, here you have your y, and then suppose you have these points in xy plane. Suppose the behavior is like this. Okay, here you have the set of points. Of course, you have some noise somewhere. What do you see? What kind of pattern do you see here? Is it a line or is it curved? If you look at the behavior of your data, you see a curved, non-linear or curved relation between these your points. So we say that, hey, this is a non-linear model. Your goal is to write down the mathematical model for this non-linear pattern. So today we're going to introduce an exponential model, write down the formula and how to interpret the scatter plot using that formula. So let us write part 1. So definition. Definition of an exponential model. We say that y equals to a times b to the x. So a is a constant, a is a number, this is just a number, times multiplied by, let me put this in parentheses so you know that they are multiplied together, b raised to x, b is another constant, another number. In this case, we say that we have an exponential model. A can be any number. We're not really worried about A. We also say A is initial value or initial amount. Initial value or initial amount. However, when it comes to B, we have these situations. For B, first of all, B is not equal to 0. B is not equal to 0. Very well. If B is greater than 1, if B is greater than 1, we call B a growth factor. B is called the growth factor. If B is sandwiched between 0 and 1, if you have a decimal number, a fraction, a small number between 0 and 1, we say that B is a decay factor. It's called the decay factor. For example, let's take a look at these examples. A, suppose you have the following. Suppose y hat is defined as 2000 times 1.95 raised to x. B, I'm giving you another exponential model. Y hat equals to 2000 times 0.95 raised to the x. We have exponential model. A is equal to 2000. Initial amount is 2000. In this case, your B is 1.95. B is 1.95. It's greater than 1. It means that our graph is increasing or we have a growth factor. So B is a growth factor. It means that your model, this model is actually an increasing model. The general behavior of the graph is going to be like this. What about this case, the second case? Just separate this for you. The initial amount is the same, 2,000. So in this case, the initial amount is the same. It's actually just 2,000. How about your B? Your B is equal to 0.95, 0.95. As you can see, this number, this decimal number is less than 1. What's the meaning of that? It means that B is going to be a decay factor. B is a decay factor. If you look at the graph, it means that the graph is a decreasing graph. The behavior of the graph is going to be like this. There we go. This is your graph. So if B is less than 1, the graph is decreasing. If B is greater than 1, it means that the graph is increasing. Investigating patterns in our data. Introduction. During the last half of 20th century, nuclear devices were tested at several sites in Nevada. During the testing, engineers exploded nuclear materials. The explosions released radioactive particles into the environment that made the area unsafe for living things. Very well. So the following data and graph provide data showing the amount of radioactivity measured in Area 2 between 1988 and 2000. Take a look at your data. So, what do we have here? On the first column, you have the year. On the second column, we have years since 1985, which is denoted by X. And on the last column, we have the area 2, and this is the measurement of your radiation. So remember that the beginning year is 1985. Let's go to the board, write this down to explain how it works. So in this example, we have the following. We have some years. The first one is 1988. The second one is 1989. I'm going to write down some of them. 1990, 1991, and so on. The rest of them. So your second column is actually years since, how many years? Years since 1985, which is denoted by variable X. Okay, so 1988 to 1985, so 1988 minus 1985 is equal to 3. So your X is equal to 3. Let me use a different color to make sure you see the connection between X and the number. So what's the amount of radiation? 1,683. Radiation. $1,683. So after 3 years of explosions, the amount of radiation is 1,683. So 1989 minus 1985, which is 4 years after the explosion. 4 years after the explosion, so 3 years after the explosion. 4 years after the explosion. What's the amount of radiation? 1,650. 1,650. 1990. So here we have 1990 minus 1985, which is equal to how many years? 5 years. So 5 years after the explosion, the amount of radiation is 1,534, and it keeps going. 1991, so here you have 6 years. It's going to be 6 years. What's the amount of radiation? It is 1,442. And so the rest of the years, the rest of the X values, the difference between that year and 1985, and finally the amount of radiation. If you look at the last row, it stops at 2000. You only have data until 2008. 2008. So how many years? 2008 minus 1985, which is equal to 23 years. So 23 years after the explosion, the amount of radiation is 600. 600. Still, it's a huge amount of radiation. Do we have information about 2009? Do we have information about 2010? Do we have information about 2020? We don't have those information yet. We don't have the measurements, and we only have these data in our collection. Very well. Let us take a look at the graph. This is our graph scatter plot, which is given to us. So here you have, okay, 5 years after the explosion, the amount of radiation is 1,534. So 5 years after the explosion, we expect the amount to be 1,534. 6 years, 7 years, 10 years, 10 years after the explosion, the amount of radiation is 1,141. So 10 years. This is this point associated to this 10 years after the explosion and the amount of radiation and so on. So do you see a linear pattern or do you see an exponential pattern which is decreasing? What do you think? Is it linear or? Very well. Our pattern is curved and it's an exponential pattern, but it is decreasing. Very good. Yes, Helen. Yes, Cynthia. Excellent. Excellent. It's an exponential pattern. Exponential pattern. So what is that exponential pattern? So this exponential pattern given to us by the following formula. We don't have to actually create the formula yet. This formula is given to us, which is y hat equals to 2,000 times 0.95 to the x. So y hat, y value. What is your y hat? 2000 initial amount, 0.95, it's actually the decay factor raised to x. So when you see a formula, you quickly think about what are these variables representing? What is your x? What would be your y hat? X is years since 1985. X is years since 1985. As you can see, these years are changing. 3 years, 4 years, 5 years, 6 years, 7 years, 8 years, 9 years, 10 years, and 23 years. Of course, we don't have the rest of the information here, but luckily for us, we have a nice formula and we can make predictions. Predictions about y hat. What is y hat? Y hat is the amount of radiation. Amount of radiation. So this is our graph. This is our exponential model. Try this. In previous lessons, you learned that the coefficient of determination, or R squared, is useful because it allows us to assess fit for linear and nonlinear models. Remember that in a least squares model, R squared is the proportion of total variability in the y variable that can be explained by the x variable. A. For the nonlinear model, R squared, or B, is equal to 0.97. Interpret this value using the information you have about area to radiation levels. B. For the exponential model, R squared is roughly 0.98. Interpret this value using the information you have about area to radiation levels. And C, for which model, linear or exponential, does X, years since 1985, better explain area to radiation levels? So to answer A, using linear model, it means that 97% of total variability in radiation levels can be explained by time. To answer B, we can say that using the exponential model, 98% of total variability in radiation levels can be explained by time. So it means that we have a better value, a larger number, 98% of total variability. That's a good number. So remember that in linear model, we get a smaller value, a smaller percentage. It means that smaller percentage of total variability can be explained by time. But if we use a different model, exponential model, 98% of total variability and radiation levels can be explained by time. So what's the conclusion? A larger proportion of total variability in radiation levels is explained by time using the second model, the model that we just defined, which is called exponential model. For number 5, we can take a look at the residual plot for the exponential model. As you can see, it's very scattered. Compare the residual plot above to the residual plot for the linear model in previous question. Do the residual plots indicate that a linear model or an exponential model is an appropriate fit for the data? Why do you think so? Let us get back to our question, previous question. and take a look at our residual. As you can see, your residual follows a pattern, and it means that it's not a good indication. But for our residual, using exponential model, we see there is no actually detectable pattern here. So we're happy about this residual model. So we say that the exponential model is the better fit for this data. Well, let's take a look at question 6. In the exponential model, y hat is 2000 times 0.95 to the x, and we learned that x represents the number of years since 1985, and y hat represents the predicted radiation level in the year being analyzed. You have a table. This table gives you years, x, and the predicted radiation level. Part A of the question says, use this model to complete the table below. B, use the exponential model to estimate when the predicted radiation level was less than 1000. And C, use the exponential model to estimate when the predicted radiation level was safe enough for people to be able to live in the area. It means that it must be 440 or less. How do the exponential model and the linear model differ in their predictions of when it will be safe to live in area 2? Very well. So let us take a look at the table here. So our first row is 1985, and we have the rest of them. We're trying to make predictions. So let's see. And we're following the formula that we have. Excellent. So what's the first year? 1985. 1985 years since 1985. So we have 1985 minus 1985, which is 0. So our x is equal to 0. X is 0. What is the radiation level or the amount of radiation? Very well. We have a nice formula. Let's use it to find this. We're going to write y hat equals to 2000 times, so 0.95 raised to x. What is our x? X is equal to 0. So I'm going to use 0 here to show you that we use 0 as the exponent. Y hat is equal to 2000 and 0.95 raised to 0. Any non-zero number raised to 0 is equal to 1. So in general, if you have a as a number and you raise it to 0, the outcome is always equal to 1. Note that a itself cannot be 0. So this value here is equal to 1. This is just 1. 2000 times 1 is 2000. Very well. We found our first level of radiation, which is 2000. We expected that to be 2000 because 2000 was initial amount at the beginning time, 0. Next year is 1986, 1 year after that. So 1986 minus 1985, which is equal to how many years? Just 1 year. So we have 1 year. It means that to find the level of radiation, we have to plug 1 into the formula for our x. So our y hat is equal to, there we go, 2000. 2000 stays the same, so we copy down 2000, and here you have 0.95 raised to x. What is x? X is equal to 1. Very well. 2000 times 0.95. What would be our value? The level of radiation, the predicted level of radiation, 1,900. So as you can see, it's decreasing. It's getting smaller and smaller. Next year, 1989. Well, 1989 minus 1985 is equal to how many years? 4 years. 4 years after the explosion, what is the level of radiation? Okay, I have 4, and I have a nice formula here. I'm going to plug that in. Then use calculator to do the calculation. So here we have y hat predicted value equals to 2000 times 0.95 raised to what exponent? I need my exponent, which is x, which is 4. Now let us do the calculation. This is equal to 1,629. 1,629. This one was 1,900. Okay. So here we have the amount of radiation. We expect this to get smaller and smaller. 1,629. Next year, 2,000. Well, 2,000. How many years after that? 2,000 minus 1985, which is equal to 15 years. 15 years. 15 years after the explosion. Your x is now 15. We have a nice formula. Let us use it. So y hat is equal to 2,000 times 0.95 raised to 15. And let us use our calculator to evaluate this. We expect this to get smaller and smaller. Very well. We have 926.6. 926.6. There we go. Yes. That seems to be true. Very well. What is our next year? 2010. 2010. So 2010 minus 1985, which is equal to 25 years. 25 years after the explosion. What is the amount of radiation? We're going to use our formula. Here we go. Y hat is equal to 2,000.95 raised to x, which is 25. Well, what is this value? It needs to be less than 900, and there we go. We have 554.8. It's getting smaller and smaller, 554.8. And finally, our predicted value for 2015. 2015. So 2015 minus 1985, which is equal to 30 years. Excellent. How about our x to be 30 years after the explosion. So let's use our calculator and our nice formula, 2000 times 0.95 raised to 30, raised to 30, and here we go. What is our value? 429.3. Amount of radiation. This is a predicted value after 30 years. Even after 30 years, it is not a very small value. It's 429.3. Very well, let's look at our table. So we found the years, we found the predicted radiation level, and let us answer the questions. It says after 14 years, after the year 1999. And for part C, after 29 years, which is after year 2014. The exponential model predicts that area 2 is safe in 2014, while the linear prediction says, hey, it's safe to go and live there in 1999. It's so dangerous. So as you can see, if you use a wrong model to make your prediction, it might be dangerous. That's why it's very important to choose the best model to make the prediction for your data.